So this is the homework for next week. Okay? So the first is to write the equation for this grade. Remember, we have to make this computational molecule, and chances are if it's like this, it's going to be 1, 1, 1, 1 minus 4.
Dr. Sloan, on the top, is that insulated? There's no numbers on the top.
Right, so first of all, Jason has a point that we need to know all the boundary. Without knowing all the boundary conditions, we will not be able to solve those problems. Those are called elliptic equations, and they need the boundary all over. So here are the boundary. The boundary is u equals 0 on the left edge, sorry, left, and u equal x cubed on the lower edge. What x cubed mean? It means that when x is 1, the solution is this. When x is 2, it's 8. So this is 1, 8, right? And this is the right edge, and this is the top edge. So you can see right edge is function of y squared, and the left and the top edge is x cubed minus 27x. A lot of students last year screw up this because they didn't see that x. Okay, that was in the final, I think. They didn't see this x, so then their number were really wrong. So if you substitute the x's, you will get exactly what are the. So at the end of the day, you have numbers all over this place, right? And so he would like you to write this equation. So of course you'll end up with what? 4 equation, 4 unknown, correct? And in second problem, he said solve those 4 equations using Gauss-Seidel. Remember Gauss-Seidel, that's the iteration. And you have to do this because you want 5s. That's not for your hand. Okay, you have to do it with Excel. The way we explained before. Basically, you would say, well, here's my x1, here's my x2, here's my x3, here's my x4. Okay, and then what are the relation? This is the initial value. He actually said start with 0 initial value, right? Start with initial guess of zeros. So that means that the first row will be 0, 0, 0, 0. Now what is, this is the first iteration. Initial guess. So you basically say, 0. Now the first results, the first iteration would be, how does Gauss-Seidel work? You will turn the equation, the 4 equation for unknown, you will turn the first equation into a formula to calculate x1. So let's imagine the first equation, say, 4x1 plus x2 plus x3 equals 7. So out of this equation, you get a formula so you will get, say, let's say it's 4x1 plus x2 plus x3 equal 10, right? So the Gauss-Seidel formulation for this is x1 is 10 minus x2 minus x3, the whole thing over minus 4, right? And this is n plus 1, and those guys are n and n. It's over the whatever number was here. So it's over 4. Alright? And say, let's say the second equation is x1 plus 4x2 plus x3 equal 7. Then what's x2? x2 equals 7 minus x1 minus x3, the whole thing over the 4. And if this is n plus 1, this is free homework problem for saying, what is this? x1 to power, or x1 of n2, you have a free homework. n plus 1. And another free homework for this guy? n. Another free homework.
Yeah, I thought there was a 1 free homework per class cap.
I said that it was 18. You said the 2 of them? No, you cannot get 2. Right. Right.
Can you just give it to me?
No. What's your name?
Brian Johnson.
I said that Etienne was the one who said it. All right, so why Brian said n and n plus 1? Right, and that's Gauss-Seidel, right? Gauss-Seidel is the one that's always using the latest technology, huh? It's updating all the time. So at this moment in time, we know the new x. We don't know the x3 yet. But guess what? When we go to the x4, every one of them will be n plus 1, n plus 1, n plus 1, because, I mean, this is the last guy at the row. Okay? So these formulae, you basically use them over here. So the new x1 would be basically, again, 10, it will, whatever we said, you know, we'll just open the bracket like this, and we'll say it's 10 minus, and if it's xn, we will pick it from the row before us. And if it's an n plus 1, we will pick it from the neighbor in this row, right? That's how you make n plus 1 and n. If you are calling the old one, you just basically go to the previous line. If it's the new one, you just basically, so what I'm trying to say is that, for example, x4 would be, let's call it, what, 10 minus, and everything would be minus the new x1, minus the new x2. See, I'm pulling them from my same row, divided by the 4 or whatever the number there. And so once you make those formulas, you basically just take this guy and copy it. Copy it for how long? Until the solution stops changing within the resolution he's asking for. He said 5s, so until 5 digits don't change anymore. Right? This is not that hard, okay, and no one has an excuse not to do it anymore. Because I mean, I'm showing it to you. Alright? And it's still so powerful. Alright? So powerful because the formulas is just the equation. So forget about all those direct methods, you know, that the iterative methods are very simple, but they are not accurate if you stop them too early. And unfortunately, a lot of the software, the commercial software, use iterative method, and they depend on you to be smart enough to figure out when to stop them. So if someone doesn't really know what's going on, you know, they tell you, well, you want the residual to be 3s or 4 or 5s, you're like, yeah, let's make it 1s, make it super fast. I find this new way to make the solution come quicker. Let's make it 1s. That basically means that you are pulling them too early. The solution is coming quicker, but it's horrible. I mean, it's really wrong. Okay? It really makes a difference because you are not solving 4 by 4. When you are solving a flow over something, or pipe, or a big control volume, you are solving millions of points together. So first, they cannot afford to do direct method, and even with the iterative method, sometimes they cannot really afford to work forever. Okay? Anyway, questions? So now, so we did this the two last time. The two new things right now is basically this equation. This is called, look at this, it's not uxx plus uyy, it's ut equal uxx. Right? And in problem 3 and problem 4, it's the same. But he's asking for two different methods that we will talk through them. So this is called parabolic method. And the solution is a little bit different. So let's see why. So that's the homework, and the quiz next week will be similar along the same lines. So method for parabolic partial differential equation. So to start with, where are those names coming from? So the equation is supposed to be any second order partial differential equation is kind of a uxx plus b say uxy plus c uyy, equal bunch of stuff over there. That's a partial differential equation second order. So it's just like a second order algebraic equation. Remember the b squared minus 4ac, and how this number determine whether we have real solution, imaginary solution, or beta solution. Well, it's along the same line. It's also b squared minus 4ac over here. that will basically determine whether it is elliptic, if it's less than 1, or parabolic, or hyperparabolic. So parabolic basically is when it's 0. Right? So when the equation is in the form of ux equal uyy, that means that this is 0. Right? And also the b is 0. So that basically means this guy is 0, and that's what make it parabolic. And the elliptic one, the uxx plus the uyy, what will happen? The b squared minus 4ac, the b is 0, and the 4ac is actually negative because it's 1 and 1. Okay? So that's the elliptic. The hyperparabolic is basically when it's uxx equal uyy, or it's minus uyy. Equal something. Alright? So it's the sign of this guy. Okay? So the form that we will deal with for a parabolic equation is basically ut equal uxx. It didn't really matter whether it's x and yy, or t and xx, or k and ll. Huh? Whatever the two variable, we will just have one of them first order and the other one is second order. The really big deal for you to why they are different, what's the big deal, is the boundary condition. So for elliptic equation, the one that we solved before, the Laplace and Poisson, which is uxx plus uyy equals 0, or uxx plus uyy equal to 7, or 7x, or 7y, those elliptic equation require boundary condition where everywhere, right? And it's why this is the case, why we couldn't solve it without knowing the boundary condition all the way, because when it was uxx plus uyy equal either 0 or a number, the computational molecule end up being something like this. You know that this guy end up being 1 and minus 2 and minus 2 and 1, and this guy end up 1 and minus 2 and 1. So basically, you end up with a computational molecule like this. And it's this shape, this relation, that basically tells you, you will not get this guy, you cannot get this guy without knowing his neighbor here, and the same thing over here, and the same thing over here, right? So graphically, you have to know the boundary, all right? Mathematically, this equation require boundary condition everywhere, all right? We did this last time. What's new today is this function, this equation, ut equal uxx, will actually involve initial condition and two boundary condition. And it will be open this way. Okay? So for example, it is really ut as this is a rate partial u partial t. What will happen with function of time? Okay? And it's some number multiplied by partial to u partial x squared. It's like your grade or your GPA in this class always depend on the two guys next to you, because you always copy from them. You don't solve anything. So, depending on the two guys next to you, if they do well, your grade will improve. If they don't do well, your grade. So, it's basically your grade in the future depend on, of course, it also depends on your initial grade, but it also depends on because of this, it depends on the two neighbors. This not just, so you see how it doesn't end? It's basically, it's marching with time, as long as you're a student, you keep going on. Or if you are basically, if you are talking about heat transfer problem, and you are basically a piece of iron sitting in a long rod, your temperature depends on the two neighbors too. If they are hot, they will make you hot. If they are cold, they will make you cold. And so if you know the initial temperature distribution, You can, initially you would know the distribution after 5 seconds, after 10 seconds, after 50 seconds, right? So those parabolic equation would require not boundary condition all over the place, no, only initially. This is the time, so obviously this is the time. So that's why at t equals 0, this is the initial condition, right? At t equals 0, this is called the initial condition. What is the temperature everywhere over here? What is the GPA of all those people in the row around me before we start solving the exam? Initially, what are the GPA? And then, this is basically the two boundary, the two extreme end, because, you know, for heat transfer problem, for example, if they are getting flux, they could actually spread the heat throughout this place. So you need those two boundaries, right? So we will see how does this guy, how does this differential equation, partial differential equation, be transferred into finite difference formula, and then, or a computational molecule, and we use that computational molecule to find the solution, all right, as function of time. So notice how the elliptic, it was just solve it once and that's it. You solve it only one time, but in those parabolic equation, you can keep solving it forever. So I cannot give you a problem like this without telling you how long you want to solve it, right? But I can give you an elliptic equation and tell you, well, here were the temperature around the plate, give me the distribution, and I wouldn't specify at any time. That's the steady state time, right? So that's what I meant by that sketch, that it's a Marshall integration, okay? And this is the place when I'm explaining what is this deal with elliptic and parabolic, okay? So it's the A and B and the C, right? And it's the B squared minus the 4AC that will determine, and so when it's UT, UXX, obviously we are missing the A, all right? So that makes this guy 0, and also the B is 0 because there is no X, there is no mixed gradient, there is no XT, all right? So the equation will be given like this: UT equal UXX. It's valid for in that domain from 0 to 1 during that rod or the spar. And here is the initial condition. You have to tell us the initial condition, and you will have to tell us the two boundary. Okay. So U0 and T, that's basically for X equals 0 and T. For all time long, what is you put it in ice here, for example, and this one you put it in a flame, so the temperature is constant. So as long as you know those two guys, you'll be able to integrate. And here is this finite difference formula. And so let's see why it's like this. So at a general point, I and G, it's still it's called I and G. Okay, again, this is time and this is X. Okay, the guy next to you is I plus 1 and G, and the guy over here is I minus 1 and G, okay? And this is I and G plus 1, okay? And so we know how to write UXX, right? You guys know how to do this. Can anyone help me? This is H and this is K. Can someone help me writing UXX?
It's U I minus 1.
U of I minus 1
J.
and J minus 2
Oh yeah, the middle. 2 where you are. 2ij
plus
2i plus 1 or 1 u.
I1 plus 1 and J, correct? Over
2
no.
k. Yeah. Or
No.
h. It'd be h since it's in the x direction.
Free homework problem for whoever tell me what's it out over. Huh?
2K.
Oh, it's 2h.
2K, no, 2H, no.
H squared.
H4?
H squared.
H squared. Can you have a free homework? Remember to put the free homework at the end before we forget. It was H squared. Right? Alright, so this is the second order. Now how about this UT? So I'm standing over here, okay? And last time what we said was UT, or the first gradient, it can be the point ahead of you minus the point below you over 2h, or 2k in this case. We don't have the point before us because let's say this is just the t equals 0. This is the first time step. Okay? So rather than using the central difference, which is accurate actually, they use the forward difference. So they will basically say that this ut is simply ui and j plus 1 minus ui and j over k. All right? Graphically, what happened is it's as if basically you are here at that point, and rather than using this as a slope or approximation of the slope, which seem okay, you are using this. That's the difference between central difference and forward difference. Right? And you can see how this is not really as good as this guy. And you are right. This is first order accurate, this is second order accurate. If this is the error of order of h here, the error here of order h squared. Okay? But they will use it like this. Okay? But now let's look what we did. So what we know is the initial value, we know them. And what we don't know is what happened at this new time step, t plus k. I mean, those are mystery for us. This is the future that we are trying to predict. And in this formula, we know this, we know this, we know everything at j. The only thing that's unknown is this. So this formula, if you apply it, you know immediately what will happen to you at the future. Okay? Because there's only one unknown in this formula. It's the u of I and j plus 1. That's why they call this the explicit method. Why it's explicit? Because the formula is explicit in ui j plus 1. It gives you immediately the ui and j plus 1. Other method will not be explicit. Other method will give us a solution implicitly. It will not be straightforward. So in the first homework, in the third homework problem, we said use the explicit method to solve this equation. He wanted to use this formula. Okay? So that's what this is, this formula that you're looking at over here. Okay? ui j plus 1 minus ui and j, 1 minus h squared. Alright. So here I'm trying to show you where did this come from. Okay? So this is actually, if you take heat transfer, you know that this is the general equation of conduction. Basically, here's the conduction, here's the unsteady term, and so in many problems when it's steady, we cancel this, but if the problem is unsteady, when this thing is being heated or being cooled, this guy stay, that's why you end up with partial differential equation. The analytical solution, as you must know by now, is horrible. You remember how we solved the wave equation and how the solution was in terms of Fourier series, and it was really big. So you should appreciate that we will solve this simply by algebraic formula, right? Again, this formula is not exactly this equation. Why? There is an error. What is the name of that error? Truncation error. If you want to make that error smaller and results to be really accurate, so that when you give the temperature distribution in around the airplane or inside the duct, if you want this to be really accurate, you have to make h really, really small and k really, really small, which basically means that you will have to do tons of calculation to be able to get this accurate solution. But since Excel is doing it for you, or later MATLAB or whatever software, you don't care. I mean, let him work for overnight. I will just go home and you will crunch the number. I'll come back, and that's better for me than actually having to do Fourier series, and right? So that's the compromise, right? That you are treating your basically pencil with the computing time on the Excel. All right? So again, those are the three unknown, or basically the future is we don't know it, and we know the initial condition and the two boundary. All right? And that's this explicit formula. And this guy in red, that's the only thing that we don't know. So how does the computational molecule look like? So, well, let's pull Ti in one side and put everything else on the other side. So see this, the delta x and the delta t, the h and the k, we can pull them together, delta t and delta x square, and let's call this tau. There also could be alpha from the equation. If the equation started with 1 over alpha, or 1 over 4, or 1 over 5, or any number here, you pull everything over here, and you call this basically tau. Right? So now the computational molecule become tau, 1 minus 2 tau, and tau and 1. Or simply this. What is tau again? It's, as you can see over here, it will end up being k over h square. Right? If you want to pull this, put them together, it will be k over h square. Or delta t over delta x square. Okay? So this is the formula after renaming tau as basically the delta t over delta x square, or the k over the h square. Right? And graphically it's like this: 1 tau, 1 minus 2 tau, and tau. Okay? So if I want to draw it nicely over here, one of this guy is 1 minus 2 tau, tau, and tau. And what is this tau again? Delta t over delta x square. Right? So, let's say the temperature is 0, 100, and 100, and we would like to know what's the temperature here in the future. Well, it's tau of this guy plus 1 minus 2 tau of this guy and tau of this guy. What is tau? That's delta t and delta over delta x square. Alright? So in the homework, well, here is the h and here is the k. So you know what is the tau. So the tau would be what? K over h square, 0.01 over 0.04. Right? What's 0.01 over 0.04? That's 1 over 4. That's 0.25. So the computational molecule for this problem is, give me one help, 1.25, 0.5, and 0.25. Right? So it will be 1.25, 0.5, 0.25. And that's interesting. Look at this. It's 0.25, 0.5, and 0.25. It's as if he's saying your temperature here, 50% depend on your effort. And 25% depending on how much you copy from the guy next to you, and 25% on the other guy. So, but at the end of the day, it's basically divided over those three guys. And as we push the delta t, if I told you this homework problem rather than using k 0.01, look at this. I want the solution at 0.08. How many times step? 8. You have to do this 8 times. So you would say, why should I have to do it, every 0.01? That will take forever. I don't want to do 8 times steps in the final exam. Let's do it only 2 times steps. Let's make the k a little bit bigger. So as you increase the k, what happened to the tau? It get bigger, right? So rather than delta t 0.01, if you make delta t 0.02, that make the tau rather than 0.25 to make it 0.5, for example. Right? It get bigger. So as you make the tau bigger, what happened? As you make delta t bigger and tau bigger, the contribution of the neighbor increase and your own contribution decrease. Basically, you are saying, as the time march by, if I'm making a really big time step, I will really forget what was my temperature. I will really depend more on the neighbors rather than me. But if tau was really, really small, because the k is really, really small, it will be like, say, 0.1 and 0.8 and 0.1. So only 10% and 10% and 0.8, depending on my thermal inertia. It's like in the very near future, my previous temperature really affect me. But in the long future, it's not really my inertia, it's the average of the two neighbors. That's what matters. Alright? And that's okay, but you know that as you push delta T higher, you are losing what? I mean, you are gaining the fact that you don't have to do 8 time steps. Now you are doing it only in 2 steps or 4 steps. But what do you lose in the process? Accuracy, right? So yes, you are getting it quicker, but your solution is not as accurate as the previous one, right? But if you become so greedy to make delta T, you say, no, I don't want do it 2 time steps. Let's do it 1 time step. Let's go 0.08. All right. So you will end up flipping this guy rather than. So the max here is, when you think about it, if you flip this to become, let's imagine tau is actually 1. Or actually, no, let's just go 0.6 even. Just 0.6. What will happen? If tau is 0.6, because you make delta T really big, 0.6, 0.6, and this become 1 minus 2 times 0.6. That's 1 minus 1.2. That become minus 0.2. Right? So 0.6, 0.6, and minus 0.2. Again, because you wanna, the formula is done so that you have 1 at the end of the day. So 0.6 of this guy and 0.6 of this guy, and minus 0.2 of your initial temperature. Your initial temperature is multiplied by minus 0.2. So I understand the fact that I could multiply by 0, basically saying, I forget what's my history, I don't know where did I come from, all that matters is my 2 neighbors. But to flip it to a minus, meaning that if I was hot, that will make me cold in the future. And if I was cold, that will make me hot in the future. That's totally unphysical. And that's when the solution, not just, I mean, we left accuracy before, we left it at the, when we switch it from 0.01 to 0.02. But now we are stepping into, not just it's not accurate, it's also unphysical. This is called unstable. So there is, those explicit methods are really nice because they are quick, but they have something called a stability criteria. That once you exceed that stability criteria, they go crazy. Not going accurate or not accurate, it's just basically crazy. And by crazy numerically, what I mean is the solution will start oscillating. So you will see basically the rod, which was supposed to be cooled, like start with a hot iron, and you put the 2 sides on water because you are quenching it. And unphysical solution will basically start showing the hot iron become colder than the water cooling it. How is that possible? And then the next time step, he will basically melt again. And then the next step, he become super cold. And then the next step, the computer blow up because the temperature is just really, really hot. I mean, he will exceed he will tell you it's 1 million degrees. This is basically the unphysical oscillation in the solution. If I plot the solution as function of time, and so say initially it was something like this, because it was like really hot, and suddenly we put this side in 0 and this side in 0, he will do something like this, and then he will do something like this, and then he will do something like this, and okay? So there is a mathematical proof to this. People have actually worked the mathematical formula for the stability criteria, but physically what I'm telling you is you cannot turn this guy into a negative. Right? You cannot make your temperature become a negative factor in your future temperature, right? So that's his stability criteria. It's basically you want to maintain this bigger than or equal to 0. It's my initial or my previous temperature. If I'm looking for uij plus 1, uij cannot be multiplied by a negative number. So 1 minus 2 tau, the whatever is here in this place, has to be greater than or equal 0. Which means tau need to be smaller than 0.5, which, realizing this tau or r or whatever is k over h squared, that basically relate k and h to square. So the consequence of something like this is that if h becomes smaller because you want to be super accurate, you don't want to do every 0.1 because there is an error involved in this, right? You want to do every point 0.01. Well, k has to drop time h square basically. So basically, so that you can maintain tau equal 0.5. And again, tau 0.5 is not accurate. That's just the limit for stability, not the limit for accuracy. All right. So in the final, sometime I ask them the question like multiple choice. I will tell them actually an explicit method is conditionally stable, unconditionally unstable, conditionally unstable. So what are all those expressions? So conditionally stable, that means there is a condition for its stability, right? That's the explicit method. Unconditionally stable, that it's always stable. That's the next method that we're going to talk about. It's called the implicit method. It's unconditionally stable. No matter what you do, whatever the arc that you pick, it will always be stable. It will never go crazy on you. The hot iron will never get colder than the water cooling it. But it's not accurate. I mean, if you make the delta K or the delta T and the delta X really, really big, of course it's not accurate. But at least you will not look like an idiot going to your boss and tell him, here, look, I managed to make the iron even get colder than the water. We have very good cooling system in our unit. So the implicit method will never give you this. But the rate by which this thing will cool, of course, will get worse and worse as you make delta T and delta X really big, right? To save time and save space, right? You are always tempted to make delta X bigger and delta T bigger, and you lose accuracy in this. All right. So this is all those instability thing that I was talking about. If you make tau 0.6, you basically will start seeing the oscillation like this in the solution. All right. So that's why this is called conditionally stable. And what is the stability criteria? It's coming from this guy need to be bigger than 0. One time also I gave them a problem that's not t with x. The equation was something like this. It was ut equal uxx plus uyy. Still partial differential equation, right? Still parabolic, by the way. And I told them write the finite difference formula for it. So they know how to do uxx and uyy, right? And today you learned how to do ut. It's the next time step minus the previous time step. So the computational molecule will look something like this. It's actually 2D in x and y, and this is basically in t. And then I asked them, what is the stability criteria for this guy, for this formula? The stability criteria for this formula is to make sure that whatever show up here need to be bigger than 0. You cannot allow this number. So it will not be 1 minus 2 tau, right? Can you guess what it will be? Chances are it will be, for a free homework problem, minus 40, and you have a free homework. So remember to put it in at the end of the day. It will be, why did you say minus 4? Because uxx will make 1 minus 2 and 1, and the uyy will make 1 minus 2 and 1. So you'll end up with basically 1 minus 4 tau. Alright? So then the stability criteria become 1 minus 4 need to be bigger than the 0. Right? Which is even make tau smaller. So tau now will not only need to be smaller than 0.5, it needs to be smaller than 0.25. Right? Good. So that's what he say here. So explicit methods are conditionally stable. Right? So again, how do you solve the problem on Excel? Well, you will have the initial condition. So the first at t equals 0, he need to provide you basically what is, let's make t equals 0 here. T equals 0 over here, and this will be x equals 0, and this will be x equal, depending on the h, 0.1, right? And x equal 0.2. So I'm making h basically 0.1, and I will get the initial condition from from this formula. He said it's x 1 minus x. X until the middle and 1 minus x after the middle. It's kind of a it looked like this when this is 0.5. So this is x and this is 1 minus x. Right? So the initial condition, basically when it's 0, that's 0. When it's 0.1, that's 0.1. When it's 0.2, that's 0.2, right? And then at t equal k, and what is the k that he picked? He said the k is, ouch, the k is 0.01. So when t is 0.01, what is the new temperature? We're going to solve them. So the initial condition will, so the bound condition will have to be imposed throughout the time. What are the two boundary? We cannot solve this problem without the two boundary, and you can tell why, right? Why we have to know the two boundary at the end of the grid? Because this guy and this guy, we cannot allow him to hit an unknown over here, right? We need always to be able to at the boundary, we need to be able to reach something that we know. So that's why all those temperature need to be given, right? And of course, all the initial value also need to be given, so that we can start from the first line and move forward. Does this make sense? Huh? So the bound condition is this. It's actually 0 at x equals 0 and 0 at x equal 1, no matter what is the t. So this basically tell me that, you know, I will have this guy equal 0 all the time, and eventually here when I go to x equal 1, what will be the temperature? 0, 0, 0, 0, 0, 0, 0, right? 0 all the way at the two boundary. Whatever the two boundary, I have to put them here. Alright, so then what is the temperature in this place? 0.25 multiplied by this, plus 0.5 multiplied by this, plus 0.25 multiplied by this. That if the k over h squared end up being 0.25, you guys have to figure out what is k over h squared. But the formula is as simple as this is 0.25 times this guy plus 0.5 times my old temperature plus 0.25 times the other neighbor. Right? What did I do wrong? It's this thing. 0.5. Ouch. It's ouch. Sorry. Yes.
You just said after you
Yeah, I have to just push this guy. Right. So see, it's, if we click here, you'll see this formula, this cell is multiplied by 2.5, this cell is multiplied by 0.5, and this one is 0.25. And actually, that's it. I will just copy this in here and here. I will just copy this formula all over, and then after I'm done with that line even, I will just pull it, and I'm done. Okay? Is that simple? Any question about this? So obviously the explicit method are really very easy to do, right? What's the problem then? It's the stability criteria. And so that forces you to make really slowly, move slowly. So that's why they invented the implicit solution or implicit method. So that method basically said, no, let's not stand in the old time, let's stand at the new time. So this equation is not written at I and j, it's written at I and j plus 1. Well, that then will mean that the partial 2 dash x squared will all be filled with the new values. That's 3 unknown. Right? 3 unknown. And for partial t partial time, it will be backward now. It will be t of I at the new time minus t of I at the old time. Okay? Why this is happening? Because rather than writing it over here at ing, you're writing it at ing plus 1. So this formula give me the new temperature, but not explicitly. It gave it to me in terms of an equation. I mean, I have the TIN plus 1 here in this equation, but together with the other two neighbors in the future too. It's basically as if I'm telling you, your grade in that exam is basically the grade, the average of your grade and the grade of the two guys also. And you tell me, I don't know either one of them. You know, I was just asking for my grade. Now you are telling me my grade is equal to the 0.5 of my grade, which I don't know. And plus 0.25 of the grade of the other guy that I don't know, and plus 0.25 of the other guy that I don't know. How is that? How is that helping me? So it's one equation, C unknown. How are we going to get out of this? How is that? The job was to get the TI in the future. So how are we going to get it out of this mess for a free homework problem? Anyone have a vision for what to do? No, we are stuck with this method. There is no other formula. This is the only tool you have. How you use this to get the temperature at the 3 points? Or in the future, we just want the temperature at the future. And this formula give me an equation in C unknown rather than giving me the temperature. I want one of you to invent this method right now. Of course, as you invented this method like 100 years ago, you would have been really famous, but it's never too late. But I'm iterating in one equation C unknown. No matter how you iterate, there's no way you will get it.
Can you guess your other value?
Huh?
Guess your other value?
Say what?
Start off as a guess. Go on.
What do you mean start other guesses?
Like, put in your unknown, like just guess.
So you're saying let's just assume TI minus 1 and TI plus 1 and from that get TI? No, that's not a good idea. Because I don't have any way to check on it. Say that again. That's a very good thinking. You get a free homework if you tell me where this equation will come from. So that approach is right, because one equation C unknown doesn't work. So the answer is get more equations. Where they are coming from? No, she's getting a free homework. Say that again. No, don't continue.
Okay.
No.
The second order partial, so then you'll find the solutions within it.
No, don't think about it. No.
So we make more points on the bench.
We'll apply.
And you had a free homework, but you already had one, so you don't qualify for another one. And so Etienne said, let's use the other points. Why you are standing here? Stand here and you'll get another new three equations, another equation, but not. Look at this. If you stand here, you get another equation, but not another 3 unknown. Because here you will have basically the old equation variable showing up again, and maybe you are at the end, you will get the boundary, which is known. So one equation by itself will not solve it. But all of them, at each one of those points, you will get 10 equation and 10 unknown.
I thought I said that.
No, I didn't hear it. Next time.
Something about boundary conditions?
You try next time. Be more explicit in your answer. So here what's going on. Right. So again, this is the formula. Okay. It looked like this. I'm just cleaning it up. So when you clean it up, the molecule look like this: minus tau, 1 plus 2 tau, minus tau. Unlike the tau, 1 minus 2 tau, and tau, this time it's minus tau, 1 plus 2 tau, and minus tau. And you can immediately tell why it is unconditionally stable. No matter what, it's stable. Why? Excellent. Who said that? Excellent. Excellent. I should have given you a free homework, but
You had held up just a little longer.
yeah. Excellent. Because you cannot have a negative. 1 plus 2 tau, no matter what is the tau, this will always be plus. Not accurate, but stable. Alright? And so again, writing it at all the grid points will actually generate a closed system of equation. And that system is basically, even if you have 100 points across this cell, this line, you know, it's a long rod and you're dividing it into 100 points, each one of these equations have only 3 variables. We call this matrix a tri-diagonal matrix. Why tri-diagonal? Because it has 3 diagonals, right? So a matrix like this, you don't solve it with Gauss-Seidel, you don't solve it with Gauss elimination or any other iterative or direct method. There's actually a procedure that's very quick for it. It's called, for a free homework problem, can you guess? Huh?
TDM.
Yeah, but what does it stand for?
Tri-diagonal matrix out.
What?
Tri-diagonal matrix out.
Algorithm. You get a free homework. Tri-diagonal matrix algorithm. There is an algorithm for solving a tri-diagonal matrix. So it's basically, and you can guess what is this tri-diagonal matrix algorithm, because every equation has only 3 unknown except the first and the last, they have only 2. It's basically back substitution. Alright? It starts with the last equation. The last equation you basically turn them into just 2 equations and 2 unknown. Every one of them turn into equation 2 unknown, and once you solve the last one, you go very quickly. And so it takes 5n steps to solve it. Alright? Okay. So again, I'm commenting that the forward difference and the backward difference, the forward that we did in the explicit method and the backward that we did in the implicit method, they are not accurate, right? The central is more accurate. So the implicit solved the stability, but it didn't solve the accuracy. So that's why this method. That's the last homework problem. How to use Crank-Nicholson method. So this is a formulation for Crank-Nicholson method. And you can see what he did. Rather than standing here and become explicit, or standing here at I and j plus 1 and becoming implicit, he stood in the middle between the 2 rows. So as a result, his 2 partial x squared become half of the solution on the top and half of the solution at the bottom. Of course, the solution at the top is all basically filled with this solution at the top. The solution at the top is filled with unknown, 3 unknown. And the solution at the bottom is given, right? And now he basically improved the accuracy by, he now claimed he has actually center difference for partial u, partial t. Right? So the computational molecule looks something like this. This is the equation to start with, right? So you will actually have to try the numbers over here yourself. But it's basically, you will find that you will have plus here, 1 plus something, or 2 plus 2r, and here 2 minus 2r. And it basically, this method will actually improve the accuracy a lot, and it's also still implicit. So every time you write it, you'll have the 3 unknown in the future, right? Out of this formula, you will have ti plus 1, ti minus 1, and ti in the future, right? So it will still produce a matrix. Okay? So in the last problem, I'm telling you this equation, solve it by Crank-Nicholson method, right? With h.1 and k.01, and find the solution at t equal 0.01. So obviously I need you just to do 1 time step, right? Because you will have to solve a matrix in the process, in the middle. So you can solve this matrix by, I don't know, Gauss iteration, Gauss-Seidel basically iterated method, or you can flip the matrix over MATLAB or something. But you will end up with a matrix that you will have to solve, right? Because just like the implicit method, you will end up with 3 equations every time you would write the equation. And again, the formula is this. right? I just didn't clean it up, so you will just have to clean it up and put the number over here yourself, right? So actually, let me help a little bit. So what do you think? Let's write the number here because I don't want you to get lost. So can anyone help? This is I and j plus 1, and this is I and j. So how do we do this? We basically pull all of them in one side, right? And we make all the unknown in the other side. So the unknown equal the known. The unknown is this guy, this guy, this guy, and let's bring this guy over here. See this 2 over tau? We probably have to bring the tau over here. This become tau, tau, minus 2 tau. And this is tau, tau, and minus 2 tau. And this just become 2 and 2. So what will show up over here? Tau, right? And this guy will be tau, and in the middle here you will have minus 2 tau, but then this guy will come, the ti n plus 1 is also here. He will come here, right? And it become minus 2 tau minus 2, right? Minus 2 tau minus 2, and then on the other side you'll have minus 2 tau I, but then so minus 2, right? And this would become, this minus 2 here would come here as plus 2 tau. So we have minus 2 plus 2 tau. And those are tau and tau. So they will go over the other side, and it's minus tau and minus tau. Right? And then it's a good idea to flip the sign. Let's flip the sign on all of them. So minus tau, plus tau, plus tau, minus tau, plus tau, plus tau, and this become 2 minus 2 tau. Right? I think it's correct. You work it out, but it will be something similar to this. Right? And so every time we write this computational molecule at a point, we will have to basically make tau minus tau of that neighbor, and 2 plus 2 tau of this guy, and minus tau of this equal to, and this will be the given values. This guy multiplied by tau, this guy multiplied by tau, and this guy multiplied by 2 minus 2 tau. Does this make sense? And we are done. Thank you so much.